Hey guys, you're on probability crash course for GCSE and iGCSE preparations. So we are within those two programs and we consider mostly foundation and higher maths or extended for iGCSE. So make sure you watch our previous video dedicated to probability exploration. So that was introduction to probability. We explored different tools like tree diagrams, Venn diagrams, how to analyze data using two-way tables and grid lines, right, and two-dimensional grids. Okay, so we considered and compared all those tools, and I indicate what's the most appropriate in each case. So for a particular case, so for example, for tossing two coins, what's the best way to represent all sample space, all possible outcomes, and probably the fast track, how to get probability of given events and very fast track. Okay, so today we're gonna go through combined events. Here is gonna be more examples dedicated to combined events, and we also considered different way of presentation and probably different solving techniques. Alright, so grab your pens, grab your papers, and let's get started. So first of all, I want to have a little comparison of dependent and independent events. Let's have a look at this example. We have basically combining events because, as you remember, combined events, when we consider combined or resultant combinations of, let's say, of several events occurring. For example, in this case, we toss the coin, we roll a dice, so we have two objects, and there are several outcomes in combinations might take place. For example, there might be head and tail for the coin, and might be 1, 2, 3, 4, 5, 6. If it's 6 face dice, right? It's fair dice. There might be 6 possible outcomes for dice. But in total and combinations, we have that sample space that represent all those 12 points over there. So, okay. But here is in comparison, I decided to show up a tree diagram. That's not full, that's not complete, because we need to determine probability of getting head and 4. So there is no need to draw up all other branches of that tree. So actually I limit myself to the coin when it has the tail, when it has the head, and to the dice as the second part and the second trial or second object in row 4. Okay, so I didn't draw all other branches. All right, so let's have a look. First of all, where is our event if we use grid line? So that's the grid line, and let's have a look. Getting head is right there, and 4 for the dice, so it's right there. So intersection is going to be here. That's simultaneously head and 4 occurred. Okay, so head and 4. This one event basically out of all 12 possibles. So how I'm finding 12? I just simply multiply the amount of all possible outcomes for dice, 6, by 2 outcomes for a coin, and I've got 12. So that's why we've got only one event out of 12, and this is the probability of getting exactly heads and 4 at just single event out of 12. Hence, the probability is 1 over 12. All right, let's have a look at tree diagram. So what we can see here, we see that the coin result should be head, and for a dice, we need to have 4. Okay, so let's set up probability for the coin. Both head and tail, they are equal. And in this case, 1 over 2 stays for each one. So on the first branch, we set up, on the first trial, when the coin is tossed, we set up 1 over 2 and 1 over 2, both for head and tail. All right, so for a dice, we've got 1, 4 out of all possible 6, so the probability is 1 over 6. All right, because we want to have both H and 4, what we can say? We can say that we need to multiply them. And hence we've got 1/2 times 1/6. In this case, the resultant probability is going to be 1/12. And that's combined probability of having H and 4. So look guys, we use two different instruments or two different tools. Here is tree diagram, and that was the grid line. And both, of course, we have the same result. However, let's have a look at the events that we have. We have combined events. In this case, they're compound. What does mean compound? They occur simultaneously, and the result is basically defined by combination of each individual result for the coin and for a dice. So that's why we can use the term compound events. So basically, for combined and compound events, we can use we can use those terms interchangeably. All right, well, we've got results here, just simple, taken one, doing just by classical calculations of probability. We taken one event that's favorable for us, that's favorable event, over a total number. And here we basically go through tree diagram, and we take an effect of combinations with the keyword and, because we want to have both H and 4 together. So in this case, we can find out that two events for coin and for dice, they are independent from each other, and in order to calculate both having head and 4 as the result, we simply need to take each individual probability for the coin of getting head, and we need to multiply by probability of having 4 on the dice. So that means we take in 1/2 and we multiply by 1/6. Okay, so that simple example show you that along a single branch for events that are actually independent from each other. So what does mean independent? That means the occurrence of each event doesn't have any influence on the occurrence of the other event. For example, what we have for the coin, the result for the coin doesn't have any effect on the result of the dice. They are independent and there is no correlation between them, all right? So that's the simple rule for independent events. To get combined probability, we just simply need to take individual probability and multiply. And this actually different tools shows some kind of proof that for combinations of probabilities, you need to do exactly that for independent events. What if events are dependent? What do you think, guys? If events are dependent, it means that the probability of the second event will be dependent on the first, on the previous one. For example, if you toss the coin and something happened, for example, you toss one single coin twice and something happened with the coin after the first throw, so that it's not fair anymore. So the second throw will definitely be dependent on how probably deformed, what sort of deformation occurred during the previous landing. For example, it might be deformed a little bit, and then the center of mass of that coin has actually shifted and it's not in the center anymore. So that, for example, to get head in the next throw is much more preferable. In this case, we are talking that the second event is dependent on the first event. So the second throw or second toss of the coin is dependent on the first one. But this is maybe a bit more complicated example. A bit easier example for understanding is simply taking several marbles from the back, from the sack. There is, let's say, 4 red and 2 green marbles in the back, and you have 2 trials of taking them out. And after taking the first marble, you withhold it, you don't put it back in the bag. Obviously, the amount of marbles is changed. So that's why the second trial will definitely be dependent on what was the first marble taken out, okay? And here is an example that can demonstrate this. So here is an example 5. What we need to do, we need to illustrate all possible outcomes when drawing 2 marbles from a bag containing several marbles. There are 5 reds, 3 green, and 2 yellow marbles. We need to calculate probability of getting 1 red and 1 green. So order doesn't matter. So it means that we satisfy with red-green or green-red combinations. So we need also to consider taking with and without replacement. So what it means, again, so if you take the first, let's say red, you withhold, you don't put it back, and that means for the second trial we have a different number of reds, so it's not 5 anymore, it's only 4 for the second trial. So that's why the probability of getting green will be definitely changed, so that the first taken out of the first marble is definitely have some influence on the second probability of getting the second marble, okay? And let's consider also what can be inferred from the way of taking the marbles. I mean, what can be inferred from taking the marbles if we have replacement and just without replacement. Here is the right time to reveal this question. So first of all, let's consider an example when we have replacement. So it means we put it back. So replacement means we put it back. All right, so the favorite way to represent that, because we don't have lots of outcomes over there, we can use tree diagram. And then I start drawing. So we've got red, green, and 2 yellow. So what I'm going to do, I'm going to set up the first trial. Let us start from there. Okay, it's going to be for red, that's going to be for green, that's going to be for, let's say, yellow. Okay, so let's mark the colors: red, green, and yellow. Okay, that was the first trial when the first marble was taken out. And let's consider the consequence scenario when we have after red, we can take again red, we can take green, and we can take yellow. After the green, we can do the same. So let's mark red, green, and yellow. And after the green, we can have the same options. Red, green, and yellow. And here is the same. So red, green, and yellow. All right. So what I'm gonna do, I probably want to, so that's the second trial. So you need to understand that here is, this region is for the second trial. So I put like second. Okay, and what I'm gonna do, I'm gonna take that and try to copy. Oh, okay. Anyway, that's good. So, and transfer right there. So just copy that. All right. Yeah, that's much better, I think. Here I can delete. So that's our sketch right now. So we have, here is without replacement, and before we have with replacement. Okay, so what I'm gonna do, I'm gonna do the following. So we have the picture, we have the sketch of our all possible outcomes in this case. And what I'm gonna do, I'm going to set a probability for each pathway. All right. So first we taken, we need to say that in total, how many marbles we have? 5, 3, and 2. We have 10 marbles in total. So that's why our denominator, if we're using the classical definition for probability, is going to be 10 everywhere, because in this case we have with replacement. Let's have a look there. So the first trial, doesn't matter with replacement or without, probability will be identical. So 5 red, that's favorable, over 10. Okay, even better, I'll use different color, say yellow one. So just 5 over 10. That stays for the first red. For the green we have 3 out of 10, and for yellow we have 2 out of 10. Of course you can make a simplify, so you can make the simplest form of a fraction, but there is no need right now. You can simplify later on. Okay, so when we taken the second, when we have the second trial and we're taking the second marble, after the first red, we might have red, green, or yellow. But because it was done with replacement, so after first taken red, we fix the color and put it back into the bag, okay? So that's why the quantity is still 10 for the second trial. It's not changing. So that's why we'll have all the same probabilities for the second trial. So we just can duplicate them and say that probability are the same. It's not, they're not changing. We just simply duplicate the first trial to each of the second trial. So if we have the first green, we do the same, 5 over 10, 3 over 10, and 2 over 10. And the same we have here, 5 over 10, 3 over 10, and the last one is 2 over 10. Okay, now we need to take scenarios that we satisfy. So which scenarios we are looking for? I mark as green one, okay? So I use that one and just indicate scenarios that we're looking for. Okay, so we need to have getting one red and one green, or it doesn't matter. So first, let's say it's going to be the first red and the second is green. So that's the first red, it's right there, and the second should be green. So we satisfy with this pass, and this is a scenario considering red and green first. Okay, so let's calculate probability of having both red and green. So what we're going to do in order to calculate probability, events basically in this case are independent. So we're just taking probability of the first one and taking probability of the second one, and we just simply multiply them. So 5 over 10 times 3 over 10, we've got 15 over 100, or just simply 0.15. That's probability of getting red and green. So that's probability for red and green combinations. All right, but we also satisfy with another combinations. Let's take another property color. So dark green, when first goes green and the second goes red. So here is our branch. So we do the same and we calculate probability as 3 over 10 times 5 over 10 in the same manner. As you can see, the probability is going to be the same. So, and actually in those types of questions, the probability, they are identical in this case. So 3 over 10, 5 over 10, we've got the same answer, 0.15, and that indicate combination green and red. All right, so in total, we consider both of them. So we satisfy red, green, or green, red. The keyword or means that we need to add those events and add probabilities so that the total resultant probability of red, green, or green, red is going to be 0.15 plus 0.15 is going to be 0.15. 13 total. So basically we add probability, and that means we add 0.15 and 0.15. So that's going to be the resulting probability. All right, let's move next and let's consider what happens if it was without replacement. It means when we first take in red or green or yellow, we withhold this marble, and hence for the second trial we have different total amount of marbles. So I just simply consider that for the first trial in total we'll have 10, but for the second trial we'll have only 9 left, no matter which color was the first marble, red, green or yellow. However, on the first trial, probabilities are going to be the same as in this case. So, because the first trial isn't identical to what we did before. So, that's why we can mark as 5/10, then 3/10, and the last one 2 yellow, so 2/10. So, look guys, for the second trial, we changed denominator of our classical probability. So that means for taking the next red, because one red is gone, we have only 4 red left. So in order to take the next red after the first red, we have only 4 reds available out of 9. Okay? For green, we still have 3 because the first was only red. So that's why for the green one, we have still 3, but out of 9. What about yellow? Still 2 out of 9. So in the same manner, we can figure out if the first was green. What about red? We still have 5 available out of 9. What about green? 1 was taken, so that means instead of 3 we have only 2, so that's why we write 2/9. That's for green. And for yellow we have still 2 available over 9. So we can repeat our speculations for when the first marble was yellow, and we've got 5/9, so 3/9, and for yellow we've got only 1/9. So as you can see, in this case, events taking the first marble and the second trial taking the second marble, they are dependent. Okay, so in case of dependent events, however, probability will be calculated as the following. So we've got probability, let's say, of event first trial and then second trial. So probability for that case will be calculated as the following. So I'll just shift a little bit. All right. We need to do the following. So we taken the first probability of the first event, first, let's say trial, first trial, and we multiply by the probability of the second trial. However, as you notice, the probability of the second trials have been changed. Instead of like 5/10, we have another probability as 4/9, and that's the different value. So that's why here for dependent events, so events are dependent, we'll have the following. So we have first probability multiplying by the probability of the second event, second trial, given that the first event occurred. So the first event occurred. That's how actually we notify that probability of the second event will be dependent on the first event, all right? However, the formula stays the same. In this case, this already has been taken into account because we changed probability. So as a result, we still need to multiply them because we need to have both, as in our question, both getting one red and the green. So we satisfy with this scenario. Let's go to our pass. So we satisfy with that one, red and green. So that's why we can simply take out probability and calculate them. So 5 over 10, we multiply by 3 over 9. In this case, it's better to take calculator, but first, maybe we can simplify, and we get 3 and 9 will be cancelled, so we'll get 5 over 30, and 5 over 30 will give us 1 over 6. So we can calculate this as well using decimals. So we've got 15 basically over 90, and it's going to be 0.16. So in this case, as you understand, we increase the chance 0.166, so 0.17. But before, if you compare with probability, we've got 0.15. So in this case, we increase the chance because probability of 4 over 9 definitely higher than 5 over 10. So you can check it out and calculate. And probability 3 over 9 definitely higher. So that's why for red-green combination, definitely there is more chance to get that. All right, well, we also satisfy with the green and then the red. So that's our combination. So green and red. So better use that one. Okay. And as a result, we can figure out that both green and red combinations will give us 3 over 10. That stays for green. And then we multiply by 5 over 9. As you might be expected, probability is going to be the same as I told you before, 0.17. And if we want to consider them both, so we satisfy with red, green, or, because there are different scenarios, red, green, or green, red. So we consider those two scenarios, the bottom one and the top one, as those which satisfy our question. So that's why in total we've got the resultant probability as 2 times 0.70. In this case we've got 0.34. And if you compare with the previous one when we got 0.30, so the final probability red green or green red, it's going to be only 0.30, while here is 0.34. Hence, you feel the difference between events that are dependent and events that are independent. So one more time, dependent events, basically events for which occurrence of one of the events does have an effect on the occurrence of the other event. In this case, they are dependent. If they're independent, basically there is no correlation between those two events, and it means you can roll the dice, you can toss the coin, they are independent. You can toss the coin many times and events again, they are independent. That's why probability is not changing, while for dependent events, probability has been changed because we taken the second trial given that the first event occurs. So there is sort of correlation. Alright, so hope you got this, and we go next. Just another examples when we have 2 marbles that taken from the back. Okay, so we've got several marbles, 4 blue and 5 green. A marble is selected and then replaced, and then the second marble is taken. So calculate the probability. So the key words here, a marble is selected and then replaced. So that means with replacement, this problem with replacement, and we can easily set up tree diagram for those combinations. All right, I'll use that one first. Okay, and I squeeze a little bit. So that's, we have 4 blue and 5 green, so we taken the first marble and then replaced. So that's why the probability, sorry, the tree diagram will look like this. So let's take, that's blue and that's green. Now we'll go next. So after the blue, my again blue, green, and here it's going to be blue, green. So blue, green, and again blue, green. All right, so that's the first trial, that's the second one. What we're going to do, we need to set up probabilities along each pass. So first, taking blue, we know that in total 4 and 5 will give us 9, so we know that in total there are 9 marbles for each trial. So that's why what we can do, we can say that we have 4 out of 9, and for the green is the rest part, 5/9. And indeed, if you add a probability 4/9 and 5/9, you'll get 1 in total. So probability in total will, if you add 2 scenarios, you notice that it's going to be 1. So what it means that event of taking the blue one is complementary to event of taking the green. So in this case, 2 events are called complementary. So basically, complementary events, you can consider probability for complementary as event, let's take taken blue, and plus event taken not blue but other is basically green. So that means PB is going to be a complement to P green. So in total, if you add them up, they need to give you 1 in total. All right, let's go to the second trial. In this case, oh, by the way, yes, I want to notice also that for basically complementary events, they form the whole sample space in the whole universe, right? So 2 events are complementary if A with not A basically form universe, will form universe. So universe is all possible outcomes that might take place within a given problem or within the context. And that means that probability PA with probability P not A is going to be always 1. So you can use that trick in order, if you want to express PA from P not A as 1 minus that. So you can basically rearrange as normal equation. All right, so we've got the second trial, and getting the next blue will have the same probability because this problem is with the replacement. So we've got 4/9, and for the green we just duplicate that 5/9. So for blue we've got 4/9 and 5/9 again for green. Okay, so we need to calculate probability that both marbles are green. Let's take up the case that we are interested in. So both marbles are green, so that means we need to have green and green branch is that one. So that's why resultant probability, you take in 5/9 and multiply by itself, 5/9 times 5/9, and you'll get 25/81. Okay, so that's probability of getting both greens. So the first is green and the second is blue. In this case, definitely we need to make sure that the first is green, it's right there, and the second is blue. So scenario that we are looking for is that one. So there's first green and the second blue. So we satisfy with that scenario, so that's why we need to multiply 5/9 by 4/9 in this case. So we have green and blue combination, so we're taking 5/9 for green and we multiply by 4/9 of blue. Okay, so in total we have 20/81. Okay, so C, there is one of each color. So which combination we satisfy? What does it mean, one of each color? It means we can have, let's say, green and blue, or we also satisfy with blue and green. So green and blue is 20/81 as we calculate in part B. So that's 20/81. And blue-green is basically the first blue, then it's green. That's the same probability if you multiply them. So 4/9 times 5/9 is again 20/81. So that's why we can simply multiply by 2. Okay? So but I write clearly, so it's 20/81. And because we have or, we just simply add them up. But this is the same as we're taking 2 multiplying by one single probability. And we've got 40/81. All right. So I hope it's pretty clear. And we go to the next problem dedicated to. So that's with the replacement. Oh yeah, it seems to me we covered that, yeah. So let's go to the next one. So we're going to consider combined events again, but here we are going to apply next tool, which is Venn diagram. So Venn diagram is very useful when you have basically a group and you have some activities, or basically this group is divided into several subgroups according to some attributes or according to some activities. So in this case, if you read the question and the problem, let's have a look. The class of 30 students, and 5 do breakdancing, 9 attend hip-hop studio, and 3 take both. Okay, so you need to show this information in Venn diagram and then determine probability, then randomly selected class students going for. And there are sort of questions here. But anyway, the first and key idea is to, sorry for that, I just need to choose an appropriate instrument so that I can do my writings. It's right there. Okay, otherwise it doesn't work for some reason. I don't know why, but okay, anyway. So, okay, first of all, let's consider how it can be dropped on the Venn diagram. We set up a rectangle. Let it be the black one. Okay, so that's rectangle. Maybe set up there so that we have something for calculation. All right, and we need to drop 2 circles indicating first circle stay for breakdancing and the second for hip hop studio. So that means we are going to set up different activities. Yeah, it's good. All right, and let's have a look how we can set up. There are 30 students in total, so we have universe, in this case, universe of 30 students. 5 do breakdancing. Let's set up the first circle for breaking and the second for hip hop. But we cannot set them up like here, because as you remember, only breaking represents students only visiting only breaking or attending only breaking. So for hip hop, that's the same story. Here, the region where that stays for students who are attending hip hop only. But we know that 3 students takes both. So that means both means breaking and hip hop, this is intersection. So that area, I'll probably shade a little with light pinky. So that means it's B intersect with H. That's what it means. This is the common part. That means they do both activities, breaking and hip hop. And there are 3 students over there. So we set up 3 immediately over there. Okay, there are 3 students who taken both. How to find who does only breaking? We know that 4 students, so we simply subtract 3 from 5 and we get 2. So in total we can check that 2 and the common part, 3, will give us 5 students who do breaking. So 3 of them just doing both activities. The same we can do with hip hop. So we have 9 students in total who attend hip hop studios. So that's why we 9 subtract 3. That's how we arrive to 6. Okay, let's combine them. 2, 3, and 6 will give us 11. So 2 plus 3 plus 6 will give us 11. That students actually do either breaking or hip hop or both. That what it means B union with H. Maybe it's better to write union like this, okay, with H. That means a combination of breaking, hip hop, and both. So that's, if you shade this region, you need to shade every single circle, and they represent 11 students. Okay, so what about 30 students? That means that 90 students don't do either any of these activities. So 9 students don't visit breaking and hip hop. All right, let's get it to the question straight away. So we have a randomly selected class student, just single one, and we need to calculate the probability that he or she goes in for both breakdancing and hip hop. How many variable students? Both breaking and hip hop, 3, right? So you divide them by, you taking them from the whole students, from the whole amount, so that's why it's 30 stays there in denominator. So that's why if we cancel, we get 1/10. All right. So here, next, at least one of breaking and hip hop. At least one of breaking or hip hop. So it might be just only breaking, it might be only hip hop 2 and 6, or it might be both, because the keyword here, at least one. So we satisfy with basically union, right? So how many students we get in total? 2, 3, and 6. 2, 3, and 6. So that's why we've got 11 over those 30. All right. So next one, that student who was selected, go in for breaking but not hip hop. So it means only breaking but not hip hop. That means only 2 students do that. That's why variable number of students over total amount, 30. So exactly one of breaking and hip hop. So exactly one, it means in this case either 2 or 6, because if we include 3, that means the student will do both B and H, but we need to have exactly 1. So that's why we satisfy with 2 plus 6 over those 30, which is actually 8 over 30, or if you want, we can cancel up to 4 over 15. All right, so neither breaking nor hip hop. Where are those students? There, neither. Okay, so neither. Yeah, sorry. Okay, it's gonna be 19 students who don't visit both hip hop and breaking. So it means So 19 over 30. And what about the last one? Hip hop, if it's known that the student takes breaking. All right, so if we know that students takes breaking, the total amount that we're going to take out of is only 5 students because 2 and 3. So we know that the student takes breaking. That's why we trying to select not from the whole amount, but from those who takes breaking. And there are only 5 students there, 2 and 3. And who does hip hop? Only 3 of them. So that's why the fraction and probability is going to be 3 over 5. All right. So we consider everything here. And I think that it's the most typical question on exams with different variations. So you might go through one more time. But we go next. Combined events and permutations. All right, so combined events and permutations, how they connected. First of all, let's clarify the term permutation. Basically, if you have distinct objects like 3 letters, like there, A, B, and C, permutations is basically a set of distinct objects that represent different ordered arrangements of these objects. So if you take 2 letters, A and B, how many combinations you might make from that? You might make only AB and BA. So only 2 possible. Those arrangements all basically represent permutations. Okay? Distinct objects, so you differ them. It's not like, 2 identical balls with the same color. So you need to have distinct objects. In this case, order of these objects matter. It means that, for example, if you have lock, right, and you want to unlock it, so that means you need to pick up a proper combination. And if the password basically contains 2 letters A and B, so probably AB will work, but BA doesn't work. So that's why order does matter. Okay, the keyword here, order does matter. All right, how we can consider the sample space and questions dedicated to different arrangements or basically permutations. Let's have a look at 3 letters A, B, and C. But for a while, I just swap this instrument for the lines. Okay. Sorry for that. Okay. So we have 3 letters A, B, and C, and we want to find out how many possible arrangements can be done from or can be made from A, B, C. So basically, we consider how many possible arrangements can be done. And there is a systematic way how you can do. For example, you can fix, I'll show you. So you can fix A on the first place, and that means the first letter is fixed. So you have an option for 2 other letters to be swapped. So that's first option right there. So this is the first option, and this is the second option. Okay, but we first decided to fix A. Okay, this is a systematic way because you never miss your combination, and that's why you list in full all combined events possible here. All right, so next one, we are going to fix another letter, letter B. All right, so in this case, letter B is fixed. Okay, letter B is fixed. And again, we can swap A and C. So the first combination is just BAC, and the second when we swap A and C, BCA. As you notice, B is still fixed on the first place. I just highlight that A fixed was in the first set, and in this case B. Okay, we'll go next, and we fixed the next letter, which is C. And then we have 2 options, CBA and CAB. because we can swap all other 2 letters. So in this case, we can have a systematic way to complete or to have all possible combinations available here. All right, so that's permutations, and that's how sometimes might be the problem and might be confusing for many students. In order to, and the problem is dedicated to permutations, you need to find out probably the whole list, the sample space for different combinations of A and B and C. When the order does matter, so in this case we consider permutation. All right, and that was systematic way. How many combinations or permutations in total we have? So A, B, C, A, C, B, B, A, C, B, C, A, C, B, A, C, A, B. We've got 6 of them. So we've got 6 of them. So that means the universe of all possible, so universe or a sample space, all possible outcomes within this context is going to be 6 different arrangements, okay? 6 different arrangements. When the order has matter, right? So it means order matters in this case. How to probably calculate just in one single, like simple operation, how to calculate how possible arrangements might be here. We've got 6, but it takes some time, right? But let's have a look. We have A, B, and C, but we first start probably from 2 letters, A and B, and we have only 2. So how to come to the formula that describes all possible outcomes that might take place in this case? We just simply use a simple idea to probably in which way we can get the first letter. So we have 2 letters, A and B, so we can choose the first letter on the first place in 2 ways. It might be A or it might be B. So for the first place, we can get in 2 ways. It's going to be either A or B. But for the second place, we have only one choice available. So that's why, because we want both of them, so both the first place and the second place, we need to multiply them because we want to have them both. So that's why we consider again and in this case we multiply. So in total we have 2 possible arrangements. What about 3 letters? So the first letter we can choose out of 3, so that's why we have 3 choices for the first place. For the second place, we have only 2 left. And for the last one, there is only 1 letter, so that's why it's going to be only 1 choice. So in total, we have 6 options or different arrangements. In mathematics, this multiplication of descending natural numbers from the maximum, so that's the maximum, that basically defines how many objects you'll have initially, up to the minimum, so up to 1. So decrease in order, basically that's the sequence of natural numbers starting from the maximum up to 1, and you multiply them. It's called n factorial. So in this case, we have 3 factorial. In this case, we have basically 2 factorial. And in general case, when we have n objects, let's say n letters, we will have n factorial in total. So that's why if we want to arrange n letters, it's going to be n factorial combinations. Let's calculate for 4 letters. Let's say A, B, C, and D. So we have 4 objects. So that's why, using the same logic, we can complete this multiplication as 4 times 3 times 2 times 1, okay? In this case, we have 4 factorials, which means if we calculate that, we got 12 times 2, 24 cases. As you understand, adding just one single letter to 3 letters, we have significant increase in possible outcomes that might have or might take the place. All right, so knowing that, that's basically, so this sort of problems for most students are really complicated, so that's why I decided to consider that problem. And actually this is going to be the last one, and let's have a look. We need to list in systematic order like we did before using letters. So we need to list in a systematic order the 24 different orders in which for person A, B, and C, and D may sit in a row. Okay, we have for person A, B, and C, A, B, C, and D. So we have 4 persons, and we need to list in systematic order the 24 different orders or arrangements in which for person A, B, and C may sit in a row. Okay, so this how we did with 3 letters. However, it's going to be really complicated for 4. Where's the number comes from? 24. As you remember, it's n factorial. So in this case, we have 4 different objects for person. And if we calculate 4 factorial, that will give us 24 different orders of how those 4 person may have sit on the bench or in a row. So that's going to be 4 times 3 times 2 times 1, right? And we get 24 possible combinations. All right, hope you understand that. But we need to list them using systematic way. Okay, so guys, what we can do? We can do the same, we can use the same approach, but for this reason, I already prepared something because it would take really a lot. Okay, you may try by your own before I drag them up. Okay, we use the same approach. First, we fixed, say, the first letter A, and hence we've got those arrangements. As you can see here, the letter A is fixed. So that's why we can say, okay, so letter A is just fixed everywhere it goes on the first place. So what about the second part? Because we have not 3 but 2. Sorry, we have not the rest number of letters. There is 3 letters. So that's why how many ways we can swap them. So if we fix the first letter, for B, C, and D, we can use 6 different ways. If we count 1, 2, 3, 4, 5, 6, indeed, we'll have 6 all other possible combinations, because I again know that for 3 letters, we have 3 factorials combination, and it gives me 4, all right? So that means that for when A fixed, we just simply need to, let's say, fix B and swap CD and DC. Then you can change B and C and put the C in after right A, and again swap B and D, DB and BD. Then we again put D as the last letter after A, and we again swap BC and CB. So that's the way, but you need to know in advance, and this is the quick way how you can check all possible combinations so that you don't mess up your combination or your arrangements. All right, so the next one, when we fix letter B, so we just put B on the first place and say, okay, we have again B staying in the first place, and for the rest 3 letters we have 3 factorial, which is 6 other possible combinations, and we use the same approach. I'm not going to repeat, so I hope you understand the logic. Then letter C is fixed, and finally letter D is on the first place. So if you multiply, this is basically like, you know, this is like a 2-dimensional grid, and you can multiply number of rows, 1, 2, 3, 4, in number of columns, 1, 2, 3, 4, 5, 6, to get 24. So if you multiply, we have basically 4 rows and 6 columns. Okay, hope you get it. And now we need to understand what to do with the question. All right, so the first question, we need to determine probability. Then when those 4 persons sit in random in a row, person A sits in one end of the row. All right, so now we're going to use that table. I'll switch to, say, the blue one. What I'm going to do right now, I'm going to choose the ways that satisfy conditions. Person A sits at one end of the row. How many combinations? So we know that the denominator is going to be 24. So we need to calculate how many combinations person A sits in one end of the row. It might be on the left hand, really left hand, so right there, or on the right hand. So in the first row, person A is on the left end of the row everywhere. So we have 6 combinations. And also it might sit on the right end. So where is that? Let's count together. So 1, 2, 3, 4, 5, and 6. So on top of that, when the person A sits on the right end of the row, we have extra 6 arrangements. Okay, so that's why until we've got 12 over 24 or just 1 over 2. So as you can see, it's pretty easy if you listed them up. So here the tool that I use is just listing. Okay. The second question, B sits in one end of the 2 middle seats. Okay. So that means person B might have a seat like this, A, B, and C, D. But the key idea is the person B sits like this, basically on the second place. Or there might be another case when person B sits on the third place. So that's why possible way is this one. Okay, so second or third place. No matter how A, C, and D are seated, okay? So we don't care about them. So that's why we just keep track where is the second or third place, and let's count the numbers. In this case, we have 24 in denominator as well, and let's count the places. Let's count the cases when B is on the second and B on the third row, on the third place in a row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we've got also 12 over 24. You can check me, but I'm sure that it's 1 over 2. All right. Question 3. A and B sit together side by side. So side by side means here is the case that A and B, they can sit this way, no matter which letter is around. Okay, so we have one letter here and one letter here. And or we also satisfy with BA case, but there are also some 2 letters there on each side. So that's why now we're looking for combinations AB and BA in the middle, okay? Oh, no, not necessarily in the middle. Sit together side by side, so it might be the case also like AB in the beginning. So just together, all right? So we can keep track of on those, they sit just together. So it might be several cases, but we want to make sure that they sit together. So that's why we're looking for combinations A and B with different cases, all right? So let's try to do this. So AB, in this case, I just take them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, we've got also 12 favorable cases over 24, which is also 1 over 2. And the last one, B, C, and D are seated together, not necessarily in that order, okay? B, C, and D. So we're looking for combinations B, C, D. Oh, for 3 letters, actually, there's going to be 6 possible combinations, but they need to sit together. All right, so we're looking for different combinations so that B, C, D will be together. All right, so I'll use the red one, and let's take up. So B, C, and D. B, C, and D here. So B, D, C, that's okay. C, B, D, that's okay. C, D, B, that's okay. So that's one also okay. Okay. So they split apart by A. Here is okay. That's okay. That's also okay. That's also okay. That's okay. And that's okay. Oh, all right, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, we've got 12 possible combinations out of 24, which is also 1 over 2. So everywhere, the probability for each scenario is going to be 1 over 2, 1 over 2, 1 over 2, 1 over 2. Okay, so this problem might be solved using the listing, and I hope you understand how it works. However, my final goal is to show you the quick way, without listing, just using the formula of permutations, how to calculate the same, how to answer the same questions. So guys, that's going to be the last trick that or shortcut that you can use on your exams. So however, if the question directly states, okay, you need to list, oops, so guys, you need to list them up and use the first approach. So I'm going to show you just how to use the very efficient way, how to use the second way without listing, just using the formula and understanding the question, okay? So we know that there are 4 letters. So in each calculations, we just simply want to take the classical definition of probability. So we define probability for each case as number of favorable out of the total number. And let's calculate immediately the total number of combinations. We've got 24, that's basically 4 factorial. So 4 factorial, or just simply 24. And let's get straight to the formula so that we can define all possible ways for the first question. So person A sits on one end of the row. So what it means that in question A, we care about case when A sits here while 3 letters follow the A, or first 3 letters and then A in the end. So we understand that for 3 letters, we can have how many possible combinations? So 3 factorial, right? We can permute them in 3 factorial ways. And here as well, 3 factorial ways. So we satisfy both. So in total, we simply have 6 and 6 together. So we have 12 ways. So that means we have 6 over there and 6 over there. That easily will give you idea of the probability that in total you've got 6 plus 6, which is 12. And you just calculate probability as 12 cases out of 24. As you understand, this way is pretty efficient, okay? So let's go to the next one. We have B sits in one end of the 2 middle seats. All right, so B sits in the middle, and in the middle sits no matter which one. So it's going to be third and the second and third place. So we can set up B on the second place. So here is going to be some letter and two letters after. Or we also satisfy that's the second place or two letters before, then B, and then another letter. So in both cases, we have 3 factorials because we can permute them, those 3 letters, in 3 factorial ways. And again, those 3 letters, A, C, and D, we can permute again in 3 factorial ways. So in total, we have the same 6 plus 6, which is 12. That means we've got 12 over 24, which is 1 over 2. Okay, case 3, we have that A and B sit together side by side. So what it means that we have the following case. So we need to have that A, B will sit together. However, how many ways for other letters? Okay, there might be the case that A, B might sit together here and then 2 letters. There might be the case, or the first letter, then AB, and the last letter. Or there might be the third case, I'll just squeeze a little bit. So there might be the third case. When we have, or the first, the second letter, and then AB. So we have 3 cases in a row, but for each case, we can swap both these letters and these letters, because AB doesn't necessarily which order they can sit, so they can sit as AB or BA. So that's why we can permute them in 2 ways, or 2 factorial, but 2 factorial is 2 times 1, which is 2. So 2 factorial ways, those letters also 2 factorials. And in total, we have the same for that and for that case. So because that's the same story with letters and the letters A and B. Okay, so that's why in total we have 3 ways of doing that. In total, we have again 24 cases. So that's why if we calculate that, we got 2 times 2 times 3, we've got 12 cases that favorable for us. That's favorable. So that's why in total, as a probability, we'll get 12 over 24, which is again 1 over 2. And the last one, B, C, and D seated together, not necessarily in that order. All right, so that means for this, we'll have the following: B, C, and D, and it might be on the first place, so the last letter is here, A, so there might be vice versa here, and B, C, and D. So we have 2 options, and for each options, B, C, and D can be permuted in 3 factorial ways, here and here. So that's why in total we've got 6 and 6, we've got 12. So we add them up. So that we've got 12 cases, and that means it's 12 over 24, which is 1 over 2. If you compare, we have the same answers. However, we got using the permutations formula, which is n factorial. When the order does matter, means combinations A, B, and BA will be different. In case when we have the, let's say, when the order doesn't matter, we need to use a different formula, so be careful with that. This actually was extra bonus for those who are interested in advanced maths. So I recommend for the students who can do listing with no problems, do listing, but guys, estimate using factorials how many combinations or how many arrangements you'll have in the end. All right, so that was the end with combined events, and probably in the next part 3 we'll go through different questions. We diversify our questions, I'll try to pick up very different so that we can practice with tree diagrams, with other ways of representing information, probably also permuting them. There might be the questions with permutations. So I hope that this video helped you. So 2 parts, actually really necessary for understanding, and for basically 2 hours in total, at least I estimate, you can cover the very necessary blocks so that you already have the tools, and then in part 3 you just need to practice. Probably we consider some miscellaneous problems. Okay, and that's it. So that was Daniel Dallas. Don't forget to subscribe, guys. Don't forget to smash the bell button. I really appreciate your comments. So share the comments in the comments what actually you would like to see, probably maybe some specific problems in probability or other topics for GCSE, iGCSE, so and any other programs. So guys, you're welcome, and peace out.